In this lecture, I want to talk about how we measure the relevance of a premise to a conclusion. And more generally, we're going to talk about how we measure the strength of an argument. Now, before we do that, let's just consider the three ways we can evaluate an object O in terms of its length. Now, if you look at this object O, there are three types of judgments you might make about the object. You might make a qualitative judgment. For example, that object is long. Second, you might be able to make a quantitative judgment. You might be able to say the length of the object is 1 meter, or 1 foot, or however you're measuring the length. And finally, you might be able to make a comparative judgment. You might be able to say object O is longer than object O prime. Now, we would like to be able to make these types of judgments, qualitative, quantitative, and comparative, about arguments. But in order to do that, we need some way to measure the strength of an argument. So given an argument with some premises and a conclusion, we need a way of assigning this a number or some set of numbers that measures the strength of that argument. So how do we do that? Well, we already know that there are two aspects of what it means for an argument to be inductively strong. So an argument with premise phi and conclusion psi is inductively strong if the premise evidentially supports the conclusion and the premise is positively relevant to the conclusion. So the conditional probability, the probability of psi given phi, that is, the probability of the conclusion given the premise, this is a way of measuring the evidential support of the argument. It's a way of measuring how much support the premise gives the conclusion. But what about the second aspect of inductively strong arguments? How do we measure the relevance of phi to psi? So it turns out that there are many different confirmation measures. That is, there are many different ways to measure how relevant phi is to psi. So here are two examples that we're going to talk about. I'm not going to give an overview of all the different confirmation measures. But here's a natural one, the difference measure. So remember that phi is positively relevant to psi. So we have an argument with premise phi, conclusion psi. We say that phi is positively relevant to psi just when the probability of psi given phi is greater than the probability of psi. Now, so a natural way to measure how relevant phi is to psi is just to look at this difference. So the difference between the probability of psi given phi minus the probability of psi. If this is greater than 0, then of course phi is positively relevant to psi. If it's equal to 0, then phi and psi are independent. And if it's less than 0, then phi is negatively relevant to psi. There's another measure called the likelihoods ratio. This one looks at the following fraction. It's the probability of phi given psi minus the probability of phi given not psi divided by the probability of phi given psi plus the probability of phi given not psi. Now, one thing I want to note, phi is the premise and psi is the conclusion. So in the difference, you're looking at the probability of the conclusion given the premise minus the probability of the conclusion. In the likelihoods ratio, you're looking at the likelihood of the premise given the conclusion. So it's the probability of the premise given the conclusion minus the probability of the premise given that the conclusion is false. So this likelihood ratio is a way of measuring, it's intended to be a way of measuring how relevant phi is to psi. So that means that if L of phi psi is greater than 0, that should imply, in particular, that phi is positively relevant to psi. That is, the probability of psi given phi must be greater than the probability of psi. So we should make sure that this is true. This is something that we should verify to make sure that we understand how these likelihood ratios work. That if L of phi psi is greater than 0, then in fact we can derive that the probability of psi given phi is greater than the probability of psi. So you might want to pause the video for a second and try to justify this to yourself. If you know L of phi psi is greater than 0, can you derive the fact that phi is positively relevant to psi? So let's do this. Let's justify this to ourselves. So L of phi psi is equal to the probability of phi given psi minus the probability of phi given not psi, divided by the probability of phi given psi minus the probability of phi given not psi. Plus the probability of phi given not psi. Now, if this is greater than 0, then the numerator must be greater than 0. Because the denominator is always positive. These conditional probabilities are always positive numbers. They're always greater than or equal to 0. So, of course, if you add two positive numbers, then the denominator is always going to be positive. So in order for L of phi psi to be greater than 0, it must be the case that the numerator is greater than 0. So let's assume that the probability of phi given psi minus the probability of phi given not psi is greater than 0. Now that means the probability of phi given psi is greater than the probability of phi given not psi. And now using the definition of conditional probability, this means that the probability of phi and psi divided by the probability of psi is greater than the probability of phi and not psi divided by the probability of not psi. Now, we're going to cross multiply, or we're going to take what's in the denominator on the right-hand side and multiply it by both sides, and what's in the denominator on the left-hand side and multiply it by both sides. So that means we know that the probability of not psi times the probability of phi and psi is greater than the probability of psi times the probability of phi and not psi. Now we remember that the probability of not psi is 1 minus the probability of psi. So what does this give us? Well, this gives us that 1 minus the probability of psi times the probability of phi and psi. So that is the probability of phi and psi minus the probability of psi times the probability of phi and psi. That's greater than the probability of psi times the probability of phi and not psi. Okay, now if we add this term to both sides, we get that the probability of phi and psi is greater than the probability of psi times the probability of phi and psi plus the probability of psi times the probability of phi and not psi. Now notice that the probability of psi occurs in both of those terms, so we can pull that out. So we get that the probability of phi and psi is greater than the probability of psi times the probability of phi and psi plus the probability of phi and not psi. So now I want you to note that what is the probability of phi and psi plus the probability of phi and not psi? So remember that that is actually equal to the probability of phi. So we get that the probability of phi and psi is greater than the probability of psi times the probability of phi. So again, that's because this sum right here is equal to the probability of phi. So now we're almost done. Notice that the probability of phi can be divided by both sides, so we get the probability of phi and psi divided by the probability of phi is greater than the probability of psi. But this is exactly what we wanted to prove. Because this fraction here, the probability of phi and psi, that's just the probability of psi given phi. And we just proved that that must be greater than the probability of psi. So if L of phi psi is greater than 0, that means that phi is in fact positively relevant to psi. So let's look at an example to see how these two measures work. So here's a stochastic truth table. And so let's just measure how relevant is P to Q. So the probability of Q given P, the probability of Q given P is equal to the probability of Q and P divided by the probability of P, which is equal to, so Q and P is true in the first row, so that's 0.2 divided by, now P is 0.2 plus 0.3, which is 0.5. So that's equal to 0.4. What about the probability of Q? Q is true in the first row and the third row, so that's 0.2 plus 0.3, that's 0.5. 0.4 minus 0.5 is negative 0.1. What about L of PQ? So the probability of P given Q is equal to, so again, that's the probability of P and Q, so that's 0.2 divided by the probability of Q, and Q is true in the first row and the third row. That's 0.2 plus 0.3, so that's 0.5. So this is equal to 0.4. So that's the probability of P given Q. What about the probability of P given not Q? Well, that's P and not Q, which is 0.3, divided by not Q, which is true at the second row and the fourth row. That's 0.3 plus 0.2. So this is 0.5. So this is equal to 0.6. So the probability of P given Q is 0.4, and the probability of P given not Q is 0.6. So this is 0.4 minus 0.6 divided by 0.4 plus 0.6. So that is equal to negative 0.2. So we see that while both of them agree that P is negatively relevant to Q, they assign different values. So it looks like P is more negatively relevant to Q than it is than D of this should be P comma Q. So this is an example of how to calculate what these two measures are. Now here's a fact. Both confirmation measures make the same qualitative judgments. That is, if according to D, phi is positively relevant to psi, that's equivalent to saying that according to L, phi is positively relevant to psi. That is, if D of phi psi is greater than 0, that'll happen if and only if L of phi psi is greater than 0. Similarly, if D says that phi and psi are independent, then L is going to say that phi and psi are independent, and vice versa. Now, what we showed in a previous slide is that D of phi psi is greater than 0 implies that L of phi psi is greater than 0. In fact, we have the other direction as well. If L of phi psi is greater than 0, that implies that D of phi psi must be greater than 0. And we have these other facts right here. So both measures agree about whether a premise is or is not positively or negatively relevant to psi. So a natural question is, which measure is better? Should we use D or L when measuring the relevance of phi to psi? Well, here are two things we would want any confirmation measure to satisfy. If we have a valid argument with premise phi and conclusion psi, and it's a non-trivial argument, what does that mean? Well, remember that P and not P, therefore Q is valid. This is valid because there's no truth value assignment that makes the premise true and the conclusion false. But the reason this is valid is for a trivial reason, namely that there just is no truth value assignment that makes the premise true, because the premise is a contradiction. So saying that phi implies psi is a valid argument non-trivially means that phi is not a contradiction. So if you have a valid argument with premise phi and conclusion psi, and phi is not a contradiction, then, of course, the relevance of phi to psi should be maximal. It should be the most relevant you could possibly be to psi, because after all, psi deductively follows from phi. Similarly, if the argument with premise phi and conclusion not psi is non-trivially deductively valid, then the relevance of phi to psi should be minimal, because phi implies the negation of psi. So phi should definitely not be positively relevant to psi. It should be maximally negatively relevant to psi. Well, here are two facts. That if phi implies psi is a valid argument, that is, if the argument with premise phi and conclusion psi is valid, and the probability of phi is greater than 0, and psi's probability falls between 0 and 1, then the difference between phi and psi, that is, the probability of psi given phi minus the probability of psi, well, that's going to be equal to the probability of not psi. And why is that? Well, if phi implies psi is deductively valid, then every row in the truth table in which phi is true, psi must also be true. So that means the conditional probability, the probability of psi given phi, must be 1. So this difference is 1 minus the probability of psi, which is the probability of not psi. You can do a similar calculation that if phi implies not psi is deductively valid, that means every row in the truth table in which phi is true, psi is in fact false. So that means the probability of psi given phi is going to be 0. So the difference between phi and psi, that's going to be minus the probability of psi, negative probability of psi. And these are not necessarily going to be maximal, because this doesn't have to be 1 or minus 1. However, for L of phi psi, when we're in the same situation, we have a deductively valid argument with premise phi and conclusion psi, then L of phi psi is actually equal to 1, which is the maximum amount of relevance that phi can have towards psi. Similarly, if the argument with premise phi and conclusion not psi is valid, so phi implies not psi is a deductive validity, then L of phi psi is minimal. The smallest value that you can assign to the relevance of phi to psi is minus 1. So let's use, for this reason, it makes more sense to use the likelihood ratios formula for measuring relevance. Now, what does that mean? That means if you give me an argument with premise phi and conclusion psi and a stochastic truth table, we can assign two numbers to this argument: the probability of psi given phi and L of phi psi. And both numbers measure some aspect of what it means to say that phi implies psi is a strong argument. Using that, we can evaluate whether or not arguments are strong or weak. We just need to evaluate it on a grid because we have two numbers. So along the x-axis here, we are measuring the evidential support of phi to psi. So if this number is above 0.5, so if we're in this half of the grid, that means phi does evidentially support psi. The argument is evidentially strong. And if we're above this line right here, that means that phi is in fact positively relevant to psi, because L of phi psi along the y-axis here is greater than 0. So if we're in this region, the gray region here, we have a strong argument because the argument is evidentially strong and positively relevant. So in this region right here, we evaluate this argument as strong because it's both positively relevant and evidentially strong.